This question is from GATE 2014 Mechanical Engineering paper, question number 31 of set 2. A cantilever beam of length capital L with uniform cross section and flexural rigidity EI is loaded uniformly by a vertical load W per unit length. The maximum vertical deflection of the beam is given by dash. So it's given that a cantilever beam is subjected to uniformly distributed load W per unit length. Unit of load is not given. We can assume it to be units per unit length. We need to find out the maximum vertical deflection of the beam. Now this is a cantilever beam. So clearly we can see that as this being the fixed end, the point that will have the maximum deflection will be the free end, which is farthest from the fixed end, because the deflection curve can be plotted like this. This will be the maximum deflection, that is deflection at free end. Let this be y or y max, which will find it out here. Now this deflection has to be remembered as a standard result, but for the sake of understanding, we'll use the double integration method to find out this deflection for this particular case. For the double integration, we have to use the deflection moment equation, which is nothing but moment at any section x by EI is equal to second order derivative of the deflection. Now by double integrating this equation, we can find out the deflection at any section xx. So let's do it. Also, we know that mx here, moment at any section xx, let the section be this, capital XX at a distance x from the free end. At the free end x is 0, x equal to 0 here, this is x equal to L. So mx will be equal to this much load, that is W into the UDL intensity W into the distance x gives us the total load, into x by 2 gives us the distance of CG of this load from the section. So we have mx to be W into x by 2, and this is creating a clockwise moment about xx on the right hand side. So we have the moment is negative, because as per convention this is the negative or hogging moment. Now by rearranging and putting the value of mx, we have EI d2y by dx square is equal to minus wx square by 2. Integrating both sides gives us EI is a constant, so it remains as it is. EI integration of d2y by dx square is dy by dx is equal to integration of this term is minus w x cube by 3, and in the denominator it is 3 into 2 6, plus the constant of integration, let that be C1. Now we need to find this unknown C1. We'll use the boundary condition that slope is 0 at x equal to L. So we have EI into slope is dy by dx, which is 0 at x equal to L, that is minus w L cube by 6 plus C1. This gives us the value of C1. C1 is equal to positive WL cube by 6. Let's put it back in the equation and then integrate again to find out the deflection. So we have our equation to be EI dy by dx is equal to minus wx cube by 6 plus wl cube by 6. Let's integrate it again on both sides. So we have EI into y is equal to minus wx raised to 4 upon 4 into 6, that is 24, plus wl cube x by 6 plus the constant of integration. Let's name it to be C2. Now to find again this unknown C2, we'll use the other boundary condition at fixed end, which is at x equal to L we will have the deflection as well 0. So by using that, we have EI into 0 is equal to minus w x is L, so we have L to the power 4 by 24 plus w L cube into L is L raised to 4 by 6 plus C2. This gives us the value of C2, as this when goes on the other side becomes WL raised to 4 by 24 minus WL raised to 4 by 6. So we have this as minus 3 by 24 WL raised to 4, which is nothing but minus WL raised to 4 by 8. Let's put this back and then find out deflection at x equal to 0. So putting this back, we have EI into y equal to minus WX to the power 4 by 24 plus WL cube x by 6 minus WL raised to 4 by 8. So now deflection at free end, that is y max, will be equal to 1 by EI into. When putting 0 in the first and second term, the terms become 0. Only term remaining is minus WL raised to 4 by 8. So it is minus WL raised to 4 by 8. Deflection that we have here is minus WL raised to 4 by 8 EI. This is negative because it is downward. So we can write the maximum deflection is WL raised to 4 by 8 EI downward. Let's go back and mark the correct option. The answer is option A, WL raised to 4 by 8 EI, and it will be downward. So the sign is not given, but it shows the direction. For further reference, you can refer to the NPTEL video, Lecture 30, Deflection of Beams 1. It is from the course Lecture Series on Strength of Materials. This course is by Professor S.K. Bhattacharya. He is from Department of Civil Engineering, IIT Kharagpur. I hope this solution will help you clear your doubt. Thank you.